Good afternoon, everyone. I'm Kavidu from University of Moratuwa, Sri Lanka, and I'm excited to share our research on evolution of cooperation in LLM-agent societies, a preliminary study done using different punishment strategies. So as an introduction, let's start with what motivated us to do the study. Autonomous agents are widely applied in domains like customer service and healthcare, and to effectively operate within multi-agent systems, they require cooperation and coordination in dynamic and often unpredictable environments. So behavior of these multi-agent systems are often modeled through game theory models and evolutionary dynamics, which are both mathematical approaches. So one of the prominent simulation study of the evolution of cooperation is well known as Boyd Richardson's work. They model cooperation through punishment-based abstract mathematical framework. So, however, these abstract models lack realism and they are often difficult to extend into complex human-like settings because of the mathematical equations and frameworks present in them. So we have now the opportunity with the rise of LLMs that are capable of natural language reasoning, and they have been shown to implicitly capture social human reasoning. So we investigate whether these LLM agents can replicate norm emergence and strategic evolution as seen in Boyd and Richardson's work. So our research focus includes modeling a realistic in-player social dilemma with using LLM agents and guided by the strategies from Boyd and Richardson's work. So let's quickly talk about what is Dinah's dilemma. So a group of agents will go to a cafe or a pub, and beforehand they will decide to split the bill equally among themselves. So one of agents can face a dilemma when they are ordering. So one of them can order a less expensive food to reduce the total bill amount. That is the corporate action here. That will increase the collective benefit of the group, while one agent can choose to go order a fancy, expensive food item and let others bear the cost for it when splitting. So this is to maximize the personal gain of that agent, considered as the defective action here. So our goal is to bridge the gap between mathematical theory and realistic agent simulations. And often these LLM studies lack meta-norms. So meta-norms is a higher level of norms which handle norm violations through punishments, and often they fail to achieve sustained cooperation over time. So with using LLM agents, we have the opportunity to make realistic decision making, reflect the strategy adaptation, as well as simulate multiple strategy combination in natural language compared to the mathematical equations present in Boyd Richardson's work. And in the long run, we can even gain insights into developing socially competent LLM agents that can behave cooperatively in multi-agent systems. So let's dive into the methodology. So first, as the environmental setup, we modified the CR6 simulation framework that uses Smallville environment from Park and others in 2023. We modeled a realistic dynasty dilemma, modifying that environment using tiled map editor. And we created new LLM agents, personas, assign them strategies from the Boyd and Richardson's work. And talking about the strategies, 4 key strategies were proposed in by Boyd and Richardson's work. They cover defection part, cooperation part, as well as a punishment part in a social dilemma. So let's quickly go through these 4 strategies. First one is called the cooperator punisher. They will always cooperate. So in a dynasty dilemma example, they will go ahead and choose a budget sandwich, and they will always punish the defective agents. And the reluctant cooperators, they will defect until being punished, but afterwards they will cooperate indefinitely. So in our example, they will start by ordering a premium sandwich, but after being punished, they will switch to a budget one. But the interesting thing is they will never punish the other agents. The easygoing cooperators, the third type, they will always cooperate similar to the cooperate punishers, but as the name suggests, they will also never punish. And the fourth and most important strategy is called moralist. They will always cooperate, but the interesting part comes in the punishment aspect, because they will not only punish the defectors, but they will also punish the non-punishers. and those who don't punish non-punishers. Though this is a higher level of meta-norm enforcement. So for example, moralists will go ahead and punish easygoing cooperators because even though they will cooperate, but they won't punish these defective agents such as reluctant cooperators, meaning that higher level of norm enforcement is needed. So moving on, our dynasty dilemma simulation process is separated out to 4 main stages, starting with the dilemma decision stage, which includes ordering, eating, and paying bills. Next, the second stage is punishment, evaluating cooperation. That is the round 1 of punishment. And the second round of punishment is the meta-norm enforcement stage. And the final stage includes calculating and updating utility of the agents and finally updating their strategies. So let's look at these 4 stages in more detail. So starting with the dilemma decision stage, while they are initiating the order, that's where the LLM comes and makes the dilemma decision. So their decision is mainly based on the strategy from the Boydell decisions model, other agents in the group, and the menu with the prices. So in our case, that is budget versus premium option. So after they have eaten and paid their bills, they move into the first round of punishments. Again, their decision is mostly based on their strategy, and they will look at the order history of other agents and decide if punishment is warranted. And third stage is called meta-norm enforcement stage, which is exclusively for the moralist agents. They will also again look at strategies and previous punishment and see whether higher level of norm enforcement is needed. And finally, they will calculate their utility based on the ordering history as well as the punishment cost P and K. So this is cost of being punished as well as cost of punishing another agent. They will calculate their utility and move on to updating their strategies. So here we use a Fermi process equation. This is a pairwise imitation process which choose a random role model from the agent population and compare the utility between the current agent and that role model and output a probability of strategy change, which is the output of this equation. And then using that, the agent can decide to adapt or imitate the other person's strategy or keep their current strategy going forward. So let's quickly look at an example from this Raj Sharma's log. So these are the actions at the different 4 stages that I explained. So starting with the dilemma decision stage, as you can see, Raj Sharma is a moralist and that agent has chosen a budget sandwich and the reasoning also matches with that. So moving on to the punishment stage, we can see Raj Sharma is punishing Jennifer Moore here, which is a reluctant cooperator, and that agent has chosen a premium sandwich. Therefore, the punishment is needed. And for the meta enforcement stage, Raj Sharma is now punishing Isabella Rodriguez, which is an easygoing cooperator here. So the reason is that person has failed to punish one defection. So because of, as I explained, this easygoing cooperator is not punishing this R1 agent. So a higher level of norm enforcement is needed to correct this Isabella Rodriguez. And finally, Raj Sharma is calculating its utility based on the ordering history as well as the punishment that agent has given. And finally, using the Fermi process equation, that output is 0.12 here. And that agent has decided not to change their strategy going forward. So in terms of the experimentation setup, as the LLM, we are using MetaLlama 3, the 70 billion instruct model. So we are using via Grok API, the free tier we are using, but we do not fine tune and we are using the base model as it is. And we have conducted a separate pre-testing. So for the 4 stages that I have described, varying LLM parameters such as temperature, topic, strategies, and even lifestyles. So the idea here is to catch and identify any biases or any inconsistencies in the outputs. So as for the number of simulations, we have conducted 6 total simulations, each with 10 iterations of repeated dynasty dilemma. The population consists of 8 total agents. So we have tested with 2 combinations of strategies. starting with the first combination, which have 2 groups, 4 agents per group. So the first combination has a moralist majority, whereas the second combination has a reluctant cooperator majority. So each combination is then repeated 3 times. So first we ask the LLM to decide P and K values. Remember, the P here is cost of being punished, K is cost of punishing another agent. So we don't provide explicit P and K here. For the second experiment, we set the ratio to 3 to 1. And for the final experiment, we further increase P value to 6. Moving to the preliminary results and discussions, we saw that LLM agents align their strategy according to their decisions with the behavioral strategy from Boyd and Richardson's work. And the dilemma decision accuracy even reached 100%, meaning that a moralist, easygoing cooperator, and cooperator punishes these cooperating strategies consistently choose budget-friendly meals, whereas the reluctant cooperators initially defected by choosing premium meals. And the punishment accuracy was also highly reliable across different strategies and conditions, again meaning that the punishment as well as the meta punishments happened and they were highly reliable. So moving on to the main results of the paper, evolution of strategy distributions across iterations. So for the first combinations where we have a moralist majority, and without explicit P and K, we can see that after 10 iterations, it has converged to a reluctant cooperator population. So this suggests that LLM did not choose sufficient P and K values enough to eliminate this defect in population. But if we further set to the P and K ratio to 3 to 1, we can quickly see that the R1 population is diminishing and the cooperator strategies such as moralist and cooperator punishers coexist at the end of the simulation. But if we further increase up to 6 to 1, we can quickly see that it even quickly converge or eliminate R1 populations, as well as it converge into even moralist strategy towards the end of the simulation. So key takeaway here is when we set explicit punishment, higher the P, higher likely to converge into a cooperative strategy and even moralist. So moving on to the second combination, we can see with a reluctant cooperator majority, same as the first combination, without explicit P and K, it converges into R1 majority. And if we increase the ratio to 3 to 1, we can see even that converge into moralist strategy as well. If we further increase up to 6 to 1, we can see similar to, or unlike the last combination, the M and P coexist here. And this is because of the randomness of the Fermi process, because that and any agent can choose any random agent as their role model. So this can vary, but converged at the end of the simulation. But overall, we can see with the higher number of reluctant cooperator majority, they can be eliminated with setting higher levels of punishments. So as for the conclusions and future works, so in terms of the contributions, we have transitions from Boyd Richardson's abstract model into LLM agents that uses natural language reasoning and Fermi-based strategy adaptations, which is a more realistic way of imitating strategies. And in terms of findings, we see that LLM agents show promising trends towards cooperation in the Diners dilemma, especially when explicit punishment costs are provided, as we saw in the results. Moreover, moralist strategies and punisher strategies dominate over time, but we saw that their convergence is influenced by the stochasticity of the Fermi process. Like we saw at the end, some moralist and punisher strategies may coexist in some experiments. And finally, the prompt design matters significantly because we are using smaller LLMs, 7 billion parameter model. So we have found that LLM agents have actions highly dependent on prompt design. So we have to be cautious when using overly lengthy or any complex prompts for reasoning. And as for the future works, we need to systematically variate and experiment with different strategy combinations. Even further P and K variations, we only tested for 3. And long iterations, we only tested for 10 iterations. We can increase to 25 iterations or 100 iterations and see what happens. And repeated experiments of the same configuration may lead to more validate into more generalizable and robust results. So these are the references that I have used, and thank you for listening, and I'm happy to take any questions. So good evening, good morning, and